So thank you for having me on Tube, and I'm very glad to have opportunity to present here about my recent project, mental AI-induced exploration in language agents. And so I'm Yulen, and I'm a second year PhD student at EPFL. And this work is a joint collaboration with Leandro Damian, and advised by my advisor Michael Moore and Maria Burbage. So yeah, and I will get started now. So here, first I will go to the background. Here, recently we have seen this paradigm shift of from developing large language models to this LM agent. The core difference is that for the large language model, you are doing this probabilistic modeling, and you care about whether you can correctly predict the next tokens. And after that, from the LM to LM agent, people care more about how can we use LM to interact with the environment. To like here, the environment can refer to like many things. It can be a tool call, a function call, can be a code. Like you can use LM to execute code, or you can use it can be a database, and LM can retrieve knowledge from the database. So it's like a rich environment. Also, it can be something like LM take actions to help you to book a ticket or to like a schedule event in your calendar. So here, with this, the LM agent is expected to solve complex multi-step problems. So the difference is, so here the difference that from the probabilistic modeling to the like agents that interact with environment by taking actions and like taking observations from the environment. Yeah, and with this LM agent has been used to solve many complex problems like coding, search engine, like playing games, or like doing some complex researches. And for the development of LM agent, people usually use supervised fine tuning or reinforced learning to train the ability of this kind of agentic ability. And so as we know recently, like this RL or reinforced learning has been playing more and more important role here. And this is also some like what we are focused in our project. So here is the background of this RL. Here we are describing this a Markovian decision process where the agents are taking actions to interact with the environment. And after that, the agents, the environment will update its state and get back to with a new observation, and also give some reward to the agent. And the goal is that to train the agents to have some maximizing the reward for the trajectory. And for language model, like what the people usually do is like is like in the framework of React. Well, like at each step, the language model will take the observation as input and output some do some chain of thought reasoning and output some action. Like here is a very brief example in a Sokoban game. You take an input as an observation with some rules and ask the model to solve the problem. He will do some chain of thought thinking and then to output the action depending on like how you define action space. And we refer to the policy this probability map between the action and the state. We use this as the policy to describe the agent. The goal of RL is to train the policy to have the maximized expected reward for this policy. So this is the background. And then when we think about RL, how we use RL to train this policy, this can be briefly described as a process of exploration and exploitation at the training time. And what this means is that still consider this Sokomo game. We only consider the first step, like the step 0, like what action will you take? Without any prior, you just have like equal probability of all actions. And what you do is like you just sample different actions and then get the reward for each actions, and then use this reward to update your policy to find the most preferred action. So I called this like the process of like you do sample and get the reward feedback from the environment. This is the process of exploration. And after that, when you export this observation to update your policy. and this is the raw process of RL. When you consider the behavior from the training time and the test time, in the training time, the agent will do this kind of exploration and exploitation. But at the test time, when there's a problem comes, the agent just directly use the learned policy. They just like a sample from the learned policy. So this means that at test time, there will not be the agent won't still explore the problem. There's no the agent just use the fixed learned policy, and no exploration happens at the test time. And the motivation is that as our human, when we see some new problems or some new tasks, we kind of do this behavior of trial and errors. Like we just attempt many times, and if it's a hard task, we probably make attempts many times, and then adapt from the previous mistakes to kind of improve. So still at the inference time, there's still a behavior of exploration and exploitation. So based on this motivation, the goal of this project is like, can we train agents to also learn to do this kind of exploration and exploitation at the test time? And we formulate this as a mental reinforcement learning problem. And here is some like a background of mental RL. So the mental RL, the mental learning means that you are doing some learning to do the reinforced learn, and it contains like an internal loop and the outer loop. So it means that in the inner loop, when you see a new problem, you do the RL training to solve this problem. And in the outer loop, you kind of do this mental learning to train the agents to quickly adapt to this problem. So and mental RL has been studied for a long period. There are many great works trying to develop this training mental RL learning framework. And here I want to especially mention this great seminal work called RL2, where they use recurrent neural network to solve the problem. They formulate this work just formulate this training process as a multi-episode training, where the early episodes is like the agents used early episode as to explore and then adapt policy in the subsequent episodes. And the agent has a hidden states shared across the environment so that they can adapt from the previous attempts. So in the area of language model, there are also several works several attempts to use mental RL to solve to train the language model. But most of this work are focused on this math reasoning task. So for this kind of task, there are the interaction of the environment is not that much, that you cannot interact with the environment and get new observations. So just kind of focusing on how you can use the concept of mental RL to have a more dense reward in the training to incentivize this better, to have better test time scaling behavior. So different from them, here we focus on the mental RL framework. That's how to train agents that can actively interact with the environment to gain observation and use that observation to adapt to the environment. So we just present a framework called Lammer for training this kind of behavior. So here we comes to the method part, and our method is actually very simple. So first, if you recall to the standard RL training, what you do is that usually you just sample multiple trajectories from your current policy, and then you just after sample the entire trajectory, you get this rewards. And then you use some training algorithm like a GRPO or PPO to optimizing your agent on the accumulated reward to find to favor the action that gives you the best reward. But here the trajectories within a group is independently sampled. So in our framework, what we do is that we just extend the single trial into the multiple episodes sequentially generated by the agent. So what we mean is that here the agent will first sample the first for the same problem. The agent will try many times, and then at each time the agent will adapt from the previous observation to adapt its policy to sample the new trajectory. So this is sequentially generated. And our intuition is that if you try multiple times, like you can just use the earlier episodes as the exploration and then you adapt your policy and to kind of try to finish the task in the subsequent episodes. So what the agent in this way, the agent what the agent will do is that it will interact in environment with a sequence of episodes. So it will try until it reaching a maximum budget or it successfully solve the task. And then after each episode, the agent will adapt its policy based on the previous experiences. So and then the training objective will be a cross episode reward, where we have a accumulated reward across different episodes, and the intuition is that if your early episode is not successful, but you find some important observation leading to the success of subsequent episodes, we should still assign some reward to these early episodes to encourage this active exploration. So that's why we have this trajectory discount factor to propagate the successful the reward in the subsequent episodes to propagate this kind of reward to the early episodes. So this is the overall training framework. And one problem is that how can we efficiently adapt the policy to the previous observation. And so in the mental health, there are some method using gradient based method to use update the policy by gradient descent. But for large language model, this would be too expensive. So what we choose to do is to leverage the self-reflection and in-context learning ability of the language model to adapt the policy. And so what we will do is that after each episode, we will prompt the agent to generate a self-reflection based on the previous episode to summarize what is wrong in the previous steps and what could be improved. And then in the next attempt, we just adapt policy by appending this reflection and the previous history in the context. Here we use this H as the inter-episode memory to adapt the policy. So within this, the benefit is that we can efficiently do the efficient adaptation without requiring any gradient. There are two important things. First, this self-reflection step is explicitly trained by using the reward of the subsequent episodes. So that in this framework, we also train the ability of adaptation by this kind of self-adaptation. The second thing is that our memory can be we can design what we put in the memory based on the efficiency or the context length of the model. Like it can be only the previous trajectories or only the self-reflection, or you can contain the both information. So this memory is very flexible. With this, we get the overall framework, and this framework can be just trained with the standard policy gradient algorithm like PPO or GRPO with this policy gradient. So this is our method. And the next I will present some our experimental results. So here is an example of what this rollout happens. So if you have if you are solving a game in the attempt 0, you just fail and then you just do a reflection. Say that I need to do to reflect the previous mistake to help you to improve, to make success in the next attempt. And the prompt, like what the prompt, like the language model will see, will look like this. So at each step, you have the state, and you do this react like this. And if it fails, you just prompt the model to do this kind of reasoning, like self-reflection, to what's wrong in the previous attempts and how to make an improved plan. And with this, you are hopefully to have some improved performance in the next attempt. So this can so that the agent can do this kind of self-improvement. Yeah, and this is some example. And then next, I will present some experimental results we have in the paper. So remember our title is mental induced exploration in language models, in language agents. So here, what we care most is the exploration ability that the agents can actively explore the environment at the test time and adapt to this observation. And how we measure the observation is by the diversity of the trajectories. So what does this mean? Is that if we have a simple game and we multiple times of the single game, if you use RL trained agents and you sample multiple solutions, you will see that it will converge to only a few solutions. But in comparison, if you take a multi agent trained by our meta RL and you sample the same solution and like sample multiple times, you'll see that the solution is much more diverse. So that the agents, like a meta RL trained agents, produce more diverse trajectories. So it can explore more in the on the environment. And if you measure the trained agents by both the exploration and by the performance, the exploration can be measured by this kind of trajectory diversity, and the performance is measured by the success rate after n attempts. You will see that the base model performs actually like is the most exploratively because it does not know anything about the environment, but it is but meanwhile it's not very good at solving the tasks. After RL training, you will see that the model kind of collapsed to a fixed policy with but kind of solve the problem to some degree. In comparison, if we train it with mental RL in our proposed framework, we see that the agent is more exploratory in a sense that the trajectory is more diverse. And meanwhile, the pass at n is also success rate at within n attempts is also higher. So the agent actually reaches a better performance between reaches a better balance between the exploration and the performance. So that's why we say that meta RL induced exploration in the language agents. And also we know that in the RL training, the diversity of the trajectory is also a very important problem. So that if you collapse to a fixed policy very early, then this policy gradient, your policy gradient algorithm probably not work as well as imagined. So this is the conceptual, like the summary of the results. And then in the experiments, we just evaluate our proposed framework in the 3 environments, like gaming environments, so Koban, Minesweeper, and the web shop. And we just report the results of like a pass at 1, 2, 3 as in the table. And we compare our algorithm with the prompting-based method, RL-based method, and our like and our like report our meta RL results. So the first thing I want to share is that if you compare the pass at 3, like the final results, we can see that our meta RL trained framework just achieved the better performance compared to all the baselines. So that it can really meaning that it really like successfully doing this kind of exploration and exploitation to reach the best final performance. The second thing is that if you compare the difference between pass at 1 and pass at 3, So you see that for the RL-based algorithm, this difference is usually kind of small. But for meta-RL algorithm, since you just can adapt from the previous experience, so the difference is usually much larger, like up to 10 or 20%. So this means that the meta-RL trained agents they can achieve better test time scaling compared to these RL algorithms. Yeah, this is so besides that, we also tested the generalization ability to harder and unseen tasks compared to the RL algorithms. And we show that the ML trained agents also has obtains better generalization to the harder and unseen tasks. Yeah, so this is the overall results we obtained in the paper. And so in summary, we just present a meta-RL framework that enables agents to actively explore and adapt from the environment at the inference time. And it reaches a better trade-off between the exploration and the performance, also generalize better to the harder and unseen tasks. And we in the paper, we just test on the simple game or like a simple embodied environment, but it can actually be extended to a broader range of tasks like a biomedical reasoning agents or like math reasoning or others. And it can also be be extended to like to find by finding a more principled strategy for exploration, or by finding some better learning signal beyond this final sparse reward. Yeah, this is the summary, and this is thank you for your time, and I'm happy to answer any questions you have.